All right, let's have a look at this homework that's due Monday. Okay, the first one's spinning a weight on a string in the vertical plane. So we're looking at having a test here a week from Monday, the 29th, I think. So one thing I'll do on the test that I may not have done in all the homework is I'll get, just to be real clear, one thing that matters is whether things are in the vertical or horizontal plane. So I'll put a little arrow on there up, just so you know it's real clear which way things are going. So what we got here, we got this weight we're spinning on a string, 600 gram for the mass of that, so that's 0.6 kilograms, 4 radians per second. We got the radius on that thing. We want to find the tension in the string, and we got a little bit of air resistance, and we want to find the rate at which the speed of the mass is changing. So what's up? Okay. So that's what we got. All right, so there, when you have a situation like that, you want to notice that it's rotating. So that very likely or definitely will involve normal acceleration. So the first thing to do here, whenever you got these, is to draw a Freebody diagram and get whatever you can on there. So when I have that weight and then a string, you know, I've got the weight, the string. Now, if you remember from static, strings are always in tension. Strings can't push, strings only pull. So we're going to have a tension like that. And that looks an awful lot like a 34-degree angle in there. Here's the tension. What else are we going to have here? We're going to have some weight, right, going down. And the weight will be whatever the mass times the gravity is. So you want to get that on there. And then you've got a bit of air resistance, and that will act counter to the motion. Okay, so that's 5.89 newtons. All right. And let's see, so the thing is going this way, right? So the velocity's doing that. Now you're gonna, whoops, I didn't draw that quite right, did I? There we go, like that. There's the velocity. Now you're gonna have a normal acceleration doing that, right? Because anytime something goes in a circle, it has an acceleration in towards the center of the circle. And then we've got some air resistance, 0.41 newtons, doing that. And then a little bit of tangential acceleration too. So we got a number of things going on there, okay? And there they are. So that's 5.89 newtons, I think. Okay. So that's a good bit of stuff on there, but that's what you want to start with. And these circular ones, I mean, there's nothing that you ever do all the time, but I think I would be most inclined on this one to have a normal and a tangential axis system up kind of like that. So I've already got the air resistance, the tension, the normal acceleration, and the tangential acceleration that are on that axis system, so that would work pretty well. I think the thing I'm going to have to work with there is the weight, and that's going to involve a little bit of trigonometry. Okay. So this is my thought process on this, okay, to kind of go through that. All right, so I'm going to get to that. So there we go. So there's that same diagram coming up there in the upper right-hand corner. What I have done is a little bit of trigonometry on that weight and gotten it resolved to components in the normal and tangential directions. So what's up there? I just used a right triangle. You know, I always want to prove this stuff out. So the top right triangle there, I'm taking the angle of that string, the cable that holds the weight. And then I know I've got a downward weight. And then I draw in a horizontal. So that gets me to a right triangle. So if I got 34 for that lower vertex angle, 90 minus 34 get me the 56, okay? That's where this is coming from. So that's the angle between the downward weight and the string. Now, once I've got that, what I'm going to do with it is I'm going to get that weight resolved into normal and tangential components is what I want to do. So now the important thing on that is the weight is the hypotenuse. The weight is the fundamental force that makes the hypotenuse of a vector triangle. And then I would want to put in the normal and tangential sides on that, knowing that the weight is the hypotenuse. So when you're coming up with these vector triangles, it's important to know what the hypotenuse is of the triangle, because that'll change how you configure the triangle. So I want that weight to be the hypotenuse. And then I'll come up with components like this. Okay. And then I know that that's 56 degrees. I derive that up above. So that's kind of my thought process on that, okay? I use the upper triangle to find the 56 degrees, but once I have it, I'm kind of carving a second little bit of a triangle in there. That sketch there is awfully small, so it's hard to get all this stuff in there, but just trying to think if I could just do it. It might help to illustrate what's going on there. Right there, I'm pulling that out, and that is this. These are the same sketches. They're both of them, okay? So that's what's going on. So I do think when you're doing these problems, getting this diagram drawn that shows all the forces and accelerations on there at their proper orientations is really important. That's more than half the work right there, is getting to that sketch of the weight. So we got any questions on accomplishing that? All right. Okay. All right. Now we got a few numbers out here still, or I'm sorry, variables. We want to find the numbers. So we want to get the velocity. That's r theta dot. You're given theta dot. You got the radius. So the velocity is 2.96 meters per second. And then we take v squared and over r, right? So that's how you would find that normal acceleration, and that's 11.84. I put it up here, which might look a little strange. Normally I put it, with the tail of the vector on the object, but I just ran out of room. I've got so much stuff on there, I just didn't have anywhere to put it, so I put it up there. Okay. And then once you got all that set up and everything's squared up on the normal and tangential axes and good to go, then, as I've kind of been harping on here, the left-hand side is the static side. That's the forces and weights. So if I'm going to go in that normal direction, okay, now the normal is on this axis right there. The tangential's coming down this way. So the normal, I've got the tension and the component of the weight, the 3.29. Now I'm also being a little conscientious here to call out the positive direction down left. Everything's going that way, so I just figured I'd call it positive. In dynamics, I tend to do that more than I might in statics. So I got the tension plus that component of the weight, and that's just equal to the mass times the normal acceleration that I calculated up here. So I can back into the tension. It's 3.81. Okay. And then the second thing to do is sum forces in the tangential direction. Forces on the left, masses and accelerations on the right. So I think that sketch is really critical to be able to solve these things. If you can just get a good sketch squared up to the axes that you're going to use, everything will just kind of come out as long as you stick with the F, the statics forces on the left and the dynamic stuff on the right. It'll just kind of come right out for you. but the challenge to me is getting that sketch. So, you got any questions on that one there? Doing all right? All right. Okay, the next one here, we got a car on a ramp. This is a little different than the one we did in class. The one we did in class, we didn't have any friction. This one we do, so we want to consider friction on this one. But the thing is, we don't know what it is. All right. So once again, you want a good free body diagram on this thing. All right, so what we're going to do with that is just kind of draw it from the front there on that view. So we got the weight down, the force of the road, which we often call the normal force, but I don't want to confuse it with my A sub n, so I call it F road. That's normal to the road. So like we drew up in that triangular example, the force normal to the road makes the ramp angle with the vertical. So that road force is going up left at 24 degrees with the vertical. So we got that. All right, now we've also got the friction. We know the coefficient of friction, but we don't know the force of the road yet. So that's going down the ramp. So it's 0.8 F road. And then we've got AM. So that's the configuration on the free body diagram. So now we want to take a good look at that. You know, we got F road, which is an unknown, and we got the normal acceleration. It looks to me like we're going to have to find the force of the road first before we find the normal acceleration, because the road's coming in from two different directions there. And this came up last time also. I think on this one I'd go with a straight sum of Fy. I don't want to go with an angled F like a force. I don't want to go with inclined axes on this. It might seem like the normal thing to do on a ramped problem, and it's often a good way to go. But on this one, I don't think it's going to work real well. And the deal is, if you do that, you're going to, when you go sum of Fy prime, you're going to pick up a component of the normal acceleration. Those accelerations are vectors, just like forces are. So if you look in the F in the Y prime direction, there is a component of acceleration going that way. Okay, so I'm going to start with sum of Fy. I'm going to have the weight down, and then cosine 24 F road up. And then I got to remember this one over here too. See, this is why we want a picture, and we just want to look at it. If you're just kind of pulling numbers and you don't have something visual behind it, you'll forget little things like that. So you got to go sine 24 times 0.8 F road, and that one's down, so that gets a negative. Okay. So this is why I want a good picture, because I can see those things when I've got a picture. All right, and I can work through that and get F road at 5781 pounds, okay? And see, that was based on a statics equation, because the thing's not accelerating up or down. It's just based on that statics equation. The only way it's accelerating is to the left on account of the normal acceleration. So you'll want to put together an equation for that and solve it, and you'll get the normal acceleration. Okay, so step one was to find step one was to get a good free body diagram, then solve it for F road, which has those two pieces to it. The force of the road plus the frictional force, which is a function of the force of the road. It's just 0.8 times the force of the road. So sum of Fy will get that. And once you've got it, you can go sum of Fx. Okay, and then you can solve for Max, and Max and Man, they're the same, or Max, yeah, and Man are the same thing. So you can solve for that normal acceleration. So this is the normal acceleration that you can have that has an equilibrium situation there. So if you're going to have any more normal acceleration, you're going to need more friction to hold the car down, basically is what's going on here, okay? So we're pushing friction to the maximum. So if that thing is going to accelerate more in the normal direction, you need more friction to hold it in. It'll start to slide up the ramp if you don't have any more available friction, okay? So what we're doing here, we can find AN and then back into the V squared over R and solve for the velocity. So that thing's going about 193 feet per second, which is 132 miles per hour. All right. So again, we're kind of seeing that need for a good free body diagram. That is really what you base a lot of your work on, is that. Okay. Questions on that one? Okay. Okay, one more. Okay, this one's, some of these problems are a little bit contrived. This one is just a little bit, I think. We've got a snowboarder here on a semicircular half pipe, I guess, 70 kilogram mass. Snowboarder starts from rest in the position shown, and then we have the velocity along the circular track then increases with a constant acceleration. So that's a constant acceleration as the snowboarder goes down the track or around the track. I don't know quite what that would be. And again, just so we all understand, that's up. Okay, that's kind of an important thing to define because it affects how gravity acts and how the weight affects the situation. So we're starting there at 27 degrees. We're going to have a constant acceleration of 2.5 meters per second squared. We want to find the force of the track at a time of 7 seconds. Right. So we got a few things to do here, I think. See, the angle that we're at matters because that's going to affect the whole free body diagram here. I mean, what you're going to have the force of the track doing that. You're going to have, what else do we got going on here? We got a little bit of normal acceleration doing that. If the snowboarder is going in a circle, we're going to have a situation kind of like this when we get down there, and it's going to be very much dependent on the angles. Okay, there's the weight. So the angle that the snowboarder's at is going to influence how you run these numbers because it's going to influence the amount of weight, okay, or the component of the weight in the normal direction. So we need to know that angle. We also need to know the velocity. Now, the thing is with this, we got constant acceleration of 2.5. So we can use that. See, we can figure out, if we know that, we can figure out two things. We can figure out how far along that track the snowboarder goes on the curved track, which we're going to have to consider. And we can also figure out the velocity. So we'll want to get this stuff worked out. So, we doing all right with that? Any questions? All right, so this has got a lot of different pieces to it, but kind of one at a time, okay? So first thing, find the mass, or excuse me, the weight. 70 kilograms times gravity gets you the weight. There we go. Second thing is find the distance along the track. Okay, S is S0 plus V0t plus 1/2 ACT squared. I think you're given the fact that the snowboarder starts from rest. So that'll get you V0, okay? And based on that, you ought to be able to find the distance. It's 61.25 meters. But the thing with this is an arc distance, okay? It's not a straight line. That's what's happening along an arc. And if you know that's an arc, you should be able to back into that angle. So what I just found there is this angle right here is 39 degrees. Okay. So 0.681 radians is 39 degrees. Okay, so I've got constant acceleration, so I don't need to do the whole calculus stuff. So what I can find with that constant acceleration is I can find the angular distance traveled along that arc, and it's 0.681 radians, which is 39 degrees. I can also find the velocity, 17.5 meters per second. All right, so now what I know is I know where the snowboarder's at, because I've got that original 27 degree angle and I add the 39 to it and I get 66 degrees. I can take that away from 90 and get 24. That gets me that angle right there. Okay? Because what's up here, and I'm kind of out of room, I guess, to put anything else, but it's kind of right in there. See, I've got 27 for the starting angle. I'm going to swing down 39 more. So that gets me a total of 66. Okay, so where the snowboarder is right there at 66 degrees. And what 66 is the original 27 plus the 39 that I calculated there with that arc distance. All right, so that gets me down here to the snowboarder. There we go. So once I've got that, now I can put together a free body diagram with the snowboarder in the proper position, 66 degrees down from the horizontal there. So if I take 90 minus 66, I get 24. That's this angle between the vertical, where the weight lies, and the normal force and the normal acceleration. So what I'm going to do there is just sum forces in the normal direction. Okay, so as I've said a number of times, I'll say it again, static stuff on the left. So the static stuff is Fn going up, but then I got to get that component of the 687 negative, and then I'll equate that on the right to MAN. Okay. I can solve for that normal force. Yeah, question there?
For that force normal equation, should that negative 627 be negative 687? Is that the weight of the skier?
Right. The weight of the snowboarder is 687, but I got to get the component of that acts in the normal direction. Right. So I'm doing a little trig on that to get to my 627.
Gotcha.
Okay. All right. So again, I got to get everything on that normal line, so to speak, that I'm calculating on. Got other questions? Or? No?
How did you get the 0.681?
Right here? Yeah, okay. What I'm doing, to get to that radian angle, what I'm doing there, I'm finding the distance along the arc. It's kind of, you're given that the snowboarder has a constant acceleration kind of on the arc of the, whatever the heck, I can't remember what it was, 2.5. So what I'm doing, I'm finding an arc distance. That's a curve distance. If you take a distance divided by the radius on an arc, you get the angle in radians.
Oh, okay.
So S over R, distance over radius. That gets you an angle in radians. So we're doing all right with that? Be right back here.
Did you stop recording?
No, it's still recording.
Nice. Just Google real quick. What do you think David looks like? He would figure it out though. Yes.
Doing all right with that? Any questions on that? All right, so we're good on that? All right, now in Moodle, I've got a little bit of an F equals MA review. Why don't we have a look at that for those of you online? All right, so here we go. So step one is to get a free body diagram. And okay, so this, you guys do this one, all right? So I'm not going to do this one for you, so you guys do this. So get a free body diagram of what? What's the free body diagram of? Yeah, the collar. Okay, so just draw a rectangle for a collar and just show the forces acting on the collar. Not what the collar does to the shaft and all that, but what those things do to the collar. Yeah, so for those of you online, just pause the recording and get that drawing made, then just start it up when we get back to it here in class. I don't want you just looking at silence here while we go through this, so just pause the recording and start it up once you got a diagram drawn.
Sounds
So 31 newtons, 58 degrees, is that right? All right, and which way does the friction go? Yeah, it goes down because the thing's moving up, so you're going to have a force of friction. Okay, you're going to have an Fn doing that, right? Because the cable's going to pull the collar to the right, so the shaft is going to push it back to the left. And that's going to be mu Fn. And then what else here? I always put the acceleration on those. I assume it's going to accelerate up. And I think I forgot the weight on there, didn't I? So 1.5 times whatever gravity is. Okay, good. See, that's why I put the up on here. Now I'll get you a review for the test probably Monday. I've got one. It's online too if you want to go look at it. What I'll give you for that is a list of topics and then also some old test problems. Okay, so that's more stuff you could do to kind of see how ready you are and all that, and learn a little bit. But the thing is, the up or down, whether it's in the vertical plane, this is in the vertical plane. This is another term I'll use for it. I've gotten pretty conscientious, so I put up arrows on there because it's real important that you know which way it's going. Of course, vertical plane, the gravity, the weight acts down, okay? If it's in the horizontal plane, that's like on a flat table, then the weight would be going into the page. That's why it's really important to specify that. So those are the terms I'll use. So vertical plane, and I'll put an up arrow on it, or horizontal plane, like a flat table. That's the words I'll use. Okay. All right. So Freebody Diagram is 14.72 newtons. All right. So what's the calculations, the sequence on the calcs to get this worked out? What's step number one there? Think in terms of unknowns. Yeah, I'd want to get that broken up. You could either, something like that, you could do it either before in the equation. That's not, that one's pretty straight up, but so yeah, you want to get that force resolved into X and Y components. And then we've got two unknowns here, right? It looks like three, but it's not. We got the force of friction, the normal, and the acceleration. The acceleration is going to depend on the friction. The friction is this mu Fn, so I think we're going to want to find Fn first. Okay, all right, and then kind of walk that over to friction, and then once you got friction, you get acceleration. That's kind of the sequence on there, right? So why don't you find the normal force next? We got a couple minutes here.
That should be a tip off. I'm off by factor like, I don't know, 90% there. Okay, I got the, okay, that's way over. How the hell did I get that? Okay, so do you get
26.29. Subtract the force of friction, which is
Cosine 58.
0.18 times 16.43 minus mg.
What'd you forget?
All over n, right?
Yeah.
I think summation of forces and that.
Right.
So you'll get to that normal. That normal is about 16.4 for the normal.
31 cosine. Oh, yeah, it's right here. 16.1.
Yeah, 31 cosine 58. Yeah.
And you get basic.
So as you work through this, you should get a normal force of, whatever the heck that is. That is 16.4.
Yes.
Okay. Okay, and then you're going to want to find the force of friction, mu times the normal, and then sum of the forces and get the acceleration. When I got to the end of this, I got about, is it 5.74 meters per second squared? Something like that. So force of friction there is 2.96. And then you can get to the acceleration after that. And that ought to be, look, I was just saying there, what the heck that is it 5.74, is that right? Yeah. That's about right. Okay, so 5.74, all right? Okay, so we'll finish this thing up on Monday, that other problem there. We'll go over this one a little bit too. Just be sure you work through this one. There's not any homework or anything right today. So Monday I'll get you a test review. That test is the week after, okay? The 29th. All right.
You said this stuff.
Yeah, the test will go up through F equals MA stuff. That's what the test will go up through. Okay.